Good afternoon to all of you. Good afternoon, Pranav. Let's start with today's work. Today we are going to start with a new chapter. Now we have done or we have almost finished two distinct topics in sound propagation, sound, or in acoustics. One is the concept of perception of sound, which is also referred as psychoacoustics. And second is the idea of production of sound. So, in the concept of perception of sound, we have covered topics like pitch, timbre, quality, consonance, dissonance, etc. And how do we measure various intensities and loudness, decibel scale, all those things. And in sound production, we have covered the topics like a musical instrument, human vocal cord, and few other ideas like loudspeakers, microphone, etc. Now, time to move ahead. Now, in this part or in this section, remember, not in this, it's not a new unit. Uh, in this section, we are going to talk about the concept of the sound propagation. How is sound propagated? Well, I will make a correction. It's a new unit. We are now getting into the third unit. So we are going to talk about first two chapters. We are going to talk about sound propagation. First is sound propagation, bit of outdoors and in the large rooms, and then we are going to talk about the sound propagation in small rooms. Later, towards the end of this unit, we are going to talk about another very important aspect of sound, and that is noise. Noise, how it is generated, how can it be controlled, what are its effects. So we are going to talk about them. So today I'm going to start with sound propagation, and first in large halls or auditoriums. So auditorium acoustics is the focus right now. Sound propagation outdoors, we will discuss a little bit. Sound propagation indoor, that is what we want to talk in detail. We are going to talk about the precedence effect, and we are going to talk about reverberant sound. Remember, you have done an experiment on that. So we are going to talk about that. Yes, good afternoon, Tejas. So, how does sound propagate outdoors? Just imagine you and your friend, you people are, say, walking on in a fairly open place, like a, say, a open garden, maybe a beach, or maybe Marine Drive, which is near our college, and you are talking to each other. Now, that is almost not perfect, but almost as good as sound propagating in a free space or outdoors. So here we can apply the free field approximation. Remember free field, we have spoken of it earlier, I think in chapter 5 or 6. A free field is one in which the sound can travel in all possible directions, 360-degree, with a constant speed or with the same speed. And remember here, we assume that the point source of sound, so the wavefronts are going to be spherical, sound pressure is inversely proportional to distance in such cases. So all open areas can be this way. Then here there is, your voice will sound different because there are no reflections. The typically it becomes a little dull sound, not even dull. uh, it becomes a very disjoint sound. One thing you will immediately notice, that if you're talking to a friend in an open space, you have to take more effort for talking for the same loudness. The reason behind it is very simple. If there are no enclosed walls or ceilings, then there is no reflection, there's no reinforcement of the sound, and therefore the sound intensity in general becomes less. You have to work harder to produce the same intensity of sound. Typically, this effect in terms of sound is labeled as sound being intimate or not intimate. So, in an indoors, the sound is more intimate, while outdoors, sound is not intimate. So, pressure is hard as usual as the distance doubles because they are inversely related to each other. And as the pressure is hard after doubling the distance, remember the intensity drops by 4 times, decibel drops by 6. Remember, if the intensity becomes a half, decibel level drop by 3, intensity decibel intensity drops by 4 times when the distance doubles, the decibel level drops by 6. Typically, this is how the graph will look like. Pressure is inversely proportional to distance. Pressure drops and level of pressure level, which is proportional to log R, will go in a straight line. What happens indoors? Now, indoors, if you have an anechoic chamber, what is an anechoic chamber? So anechoic chamber typically is a chamber where the walls are so designed that they absorb all the sound. They do not reflect back any sound. So if the walls absorb all the sounds, then the source of sound which can be assumed to be a point source of sound. It can emit sound in all possible directions, and the room becomes a free field because there is no reflection. Anechoic means there are no echoes, no echoes are there. But unless the room is designed that way, last year some students took a project in our department and they did design a small anechoic chamber. So unless the room is designed that way, the rooms are not anechoic, and the reflections are going to happen in various ways. There could be various orientation between the reflecting surfaces and the sound source, and there could be different types of reflecting surfaces. This is a straight, this is a curved reflecting surface, this is a concave, this is convex, and this is some zigzag. Typically, a zigzag is more preferred because these offer a very directional reflections. So unless like you are in some gallery in say Bijapur where the dome's wall reflect from one point to other. I have been there, and if you happen to go there, please do visit. So these are the 2 points in the dome in the gallery of the Bijapur the monument. I guess it's called Gol Gumbad or something. So if you talk very uh, in a very low voice at one end, the sound is reflected and reaches to the person standing diametrically opposite to you. So that is how the sound travels there. But this kind of surfaces offer very focused reflection. Typically, in an auditorium, this kind of roof is preferred, where the reflection is zigzag. Although also sound absorbers are placed, so the sound absorption is going to happen in a room. So for example, in a room, people sitting there will absorb sound, clothes absorb sound, the bed sheets absorb sound, curtains are going to absorb sound. If there is a sofa, upholstery, etc., they are all going to absorb sound. So sound is going to be absorbed everywhere apart from being reflected. And indoors, sound propagation is very complicated. Outdoors, it's almost a free field. Now, what happens in indoors? Let's explore more carefully with a mind of a medium to large size auditorium. Take a medium sized, like our MMR multimedia room, to a large size auditorium like our hall, college hall. Now, once the person is speaking or some music is being played, then the direct sound reaches to the people in 20 to 200 millisecond, depending upon where they are sitting. So if they are sitting closer, the sound will reach quickly in 20 millisecond. If they are sitting far, the sound will reach to them in a larger time, and it can extend up to 200 milliseconds. However, there are going to be, apart from the direct sound, there are going to be first reflection. The first reflections are called as prominent reflections or early reflections. Remember, that is what is the the first or prominent reflection. They run into the range of 50 to 80 millisecond, and it really depends where you are sitting. For example, if you are sitting in the front of the hall, then maybe the reflection will come from the side walls. Sound go to the side wall, hits and comes back. Because maybe if it's a large auditorium, the height could be much larger and the width of the wall could be, distance from the center to the side wall could be less. So that could be your early reflection. But if you are sitting somewhere, say in the middle of the hall, then the reflection coming from the ceiling could be your first and early reflection. And if you are sitting at the rear seat, near the rear seat of the rear side of the hall, in that case, the reflections coming from the back wall are going to be your first and early reflections. The first and early reflections, they differ in their directions depending upon where you are sitting in the auditorium. So, and they run into the range of a time range of 50 to 80 milliseconds. So if, for example, if the direct sound is 20, this could be go to 50, 60, 70, 80, whatever. After that, the multiple reflections will set in. The sound will reflect in multiple directions, in multiple ways, and number of reflections. So typically what happens is the person sitting in the auditorium can detect the direct sound very easily. He or she can detect the prominent or early reflections also easily, but it's very difficult to judge the reflections which come after that because they are multiple and they all mix into each other, giving you a very complex and muddled sound. This kind of sound, due to the multiple reflections, which is complex, muddles, unidentifiable in cases, is called as reverberant star sound. You know that you have already done one experiment on this, so we are talking the same thing. Here is the here is the possible geometry. People sitting here. This is the source of the sound. The sound goes direct. Sound can go from the ceiling. It can be reflected from the back wall and come, and it can go to the, you can say this is at the side wall and come. Depending on where a person sits, the timings will be determined. If the person plots a graph, the observer here plots the graph of sound pressure, then what the observer will see that the loudest was the direct sound. The direct sound was the loudest intensity. This is the impulse. This is when the sound is created, and this is the direct sound. So, of course, the direct sound will have an intensity less than the impulse. But remember, the person is not listening the impulse. The first perception of impulse is through the direct sound. And after that, the reflections, at each reflection, some amount of energy can be absorbed by the walls. and surfaces. We have seen it in our reverberation experiment. Some amount of sound or energy can be absorbed, and therefore, after multiple reflections, the intensity keeps dropping, dropping, and dropping. Precedence effect is something which is very interesting. How do the human auditory system maintain direction of sound if there are reflections and multiple reflections? So direct sound, how it keeps the direction. If it's a low frequency direct sound, then it is going to be the diffraction effect that helps us to understand the direction of the sound. If it's a high frequency, then it is the loss in the intensity value. Like if the sound is coming from the left ear will hear it loud, right ear will hear it weaker, not so loud. And because of that, we can sense the direction of sound. If it's a low frequency sound, direct sound, then the diffraction takes place, but then the time delay happens. One side it is fast, other side it is slow after some time. But what happens if there are multiple sound, multiple reflections? Then in that case, how does the human auditory system keeps track of directions? So we employ something here called as precedence effects, and it's a wonderful idea. Now, what it says that the auditory system determines the direction of sound by looking at what is the direct sound and what are the reflected sound. Now, if the direct sound and reflected sound are within 5 milliseconds of each other, or if the first reflected sound is louder than the direct sound, or if it does not have the same frequency envelope, then in that case auditory system rejects it, and direction of sound is just only on the basis of the direct sound. So this is what is called as the precedence effect. In short, the auditory system keeps reducing the direction of sound if successive sound around within 20 milliseconds. So first sound, direct sound, and the first reflection, there has to be a gap of around 20 milliseconds. The successive sound has a spectra and time envelope similar to the first sound. So the spectrum, the, the way the first sound is heard, kind of frequency component direct sound has, same type of frequency component must be there in the reflected sound, first reflected sound. And the reflected sound must not be louder than the direct sound. We have seen in the earlier graph, as the reflections grow, the amplitude drops. The world's leading concert hall has delay time between direct and first reflected sound less than 20 milliseconds for being, as I had put, intimate. So just imagine, you are in a concert hall and the time delay is more than 20 milliseconds. Then human ear will perceive direct sound and the reflected sound separate. And in that case, it will be a problem. So normally the design is such that the first reflected sound has a very small separation between the main direct sound. Such theaters are called intimate, sound-wise intimate theaters. Do remember that in our Xavier's first quadrangle, we have our Janfest happening. So during the Janfest, we had made one recording and we had checked that in Xavier's first quadrangle, the distance of the or the time for the first early reflection is as large as 1000 milliseconds. So it has a very, very large reflection of sound at around 1000 milliseconds. So not so suitable for music. Coming to the last part, and that is what is called as reverberant time. We have already discussed this. The sound in a room as the sound source plays first direct, then early reflections, and then multiple reflections from multiple surfaces. And of course, surfaces will absorb, but, but still the reflections continue and the sound energy level rise in the room. Typically, if I have a source of sound which is not playing up till here and suddenly starts playing and then becomes constant amplitude. But the sound level in the room will not vary according to this. What sound level will do, it will rise. Then original, since the source is being all played, that level remains, but the first reflection adds up. So energy increases. Then the second reflection adds up, second energy increase, so on and so forth. So if the surfaces are not absorbing much, the sound energy level keep on rising until it reaches to a maximum equilibrium where the sound energy level becomes constant as compared to the sound level of the source. Now, once the source is cut off, then the source of sound is gone, only reflections are remaining. Now, remember, at every reflection, the objects in the hall are going to absorb some sound, and therefore the sound intensity slowly starts dropping. The sound level starts dropping after the source. Most of the time it is a linear drop, and it matters whether the source is, whether the hall is occupied or unoccupied. You can see that here is the drop in an impulsive sound. This is an impulsive sound which is dropping in the room. You have plot the same graph or similar graph using Audacity. Here are two graphs, sound pressure level versus time, for an occupied and unoccupied room. So if it's an occupied by 50%, it has a different slope. That means the sound, you can see it's a higher slope than this one. That means the sound is absorbed quickly if human beings are present. Sound is absorbed slowly when human beings are absent. So reverberant time, we know that it's going to be very important consideration for a given acoustical hall, auditorium, room, etc. Mid-band reverberations are important, 500 to 2000 hertz. Majority of the musical instruments, sharp musical instruments are going to play in that. Typically, the low frequency instruments, if they are playing in with a little higher reverberant time, they tend to remain pleasant. But the high frequency instruments, they become too harsh if there is a reverberant time more than what is specified. So as we have discussed, the reverberant sound will grow because of the multiple reflections, and when the source is cut off, decay is going to take place. Reverberant level is reached when the rate of energy supplied is the rate of absorption of energy in the room. So we have seen in the earlier graph, the graph becomes almost horizontal, and that level is called reverberant level. So what does it happen? It adds sound loudness. Sound loudness increases. It is generally more loud, but it may result in the loss of clarity. So in a closed environment where some reverberation is present, talking becomes easy, effortless, because you have to produce less sound, less volume of sound, but it may lead to a loss in clarity, particularly if the reverberation time is extremely large. Electronic reinforcement of direct sound is done in order to produce reverberation. Some of the theaters may not have reverberation much, So we may produce or we may apply another sound source which is slightly delayed from the first one to mimic reverberation in a room. In general, reverberation time is defined as the time required for sound pressure level to decay by 60 dB. So this all we have learned earlier in our practical, so nothing new. In a bare room where all the surfaces absorb the same fraction of sound offered to them, their reverberation time is K into volume upon area, where all the surfaces have the same fraction of sound offered to them. They absorb the same fraction. That means the coefficient of absorption of sound is same. Then this is your general formula. Larger rooms, remember RT depends on the volume, inversely proportional to area. So if volume increases, the reverberation time increases. Remember, if volume increases, area also increases, but not in the same proportion. So we will talk more about reverberation time in the next class, but in this I'm going to show you, I've shown you already this right side video. This right side video, the door which is shown in the right side video is here. This is a cave in Rajmachi Mountains and we stumbled across it. So this is myself sitting in front of it. We had no source of sound to make, but I made a sharp sound with my mouth. And here is the long lingering reverberation of that sound. Please listen to it. So you could hear that it was a long reverberation, fairly long reverberation time. And if you talk or sing in such a reverberant environment, it's a cave with harsh stones on all sides. And if you uh, talk or sing, the sound will be very, very muddled and nothing will come clear. So that example is here. Our favorite professor tried to hum a few lines and I had the good blessings to record that. So you could see that the words are not clear. You could see that his words are not clear, and that's because the harsh room that has been shown, which has a very large, very less coefficient of absorption. It was a very classic place where you can stand outside the room, talk or sing, and go inside and talk and sing and see the difference in the two sound outputs and way it could be perceived. So, anyways, we can stop this lecture here. In the next class, I'm going to talk more on reverberation, some of its calculations, etc., and then some problems. So, thank you.